Okay, this is going to be our third video in our electric potential series, and in this video I'm going to be focusing on section 23.3, and I'm pretty much exclusively going to be doing examples from that section. Pretty much the whole section is just examples in the textbook. I'm going to do all the examples that they do, save for the very last one, which I'm going to do in our meeting on Wednesday. Okay, and so let's get started here. So in section 23.3, they start off with an example where they look at the charge conducting sphere problem, and they're looking for the electric potential outside of a charged conducting sphere. So we've looked at the electric field outside of a charged conducting sphere before, and now we're kind of going to turn the problem around here, and we're going to look at the potential for every point inside and outside of a conducting sphere with some charge on it. Okay, so we have a solid conducting sphere of radius r, and it has a total charge of q on it. We want to find the electric potential everywhere, both inside or both outside and inside of the sphere. So when we think of a conducting sphere, we want to have in our mind this idea of all the charge sitting at the surface, right? So we know that all of our charge Q is going to be sitting at the surface of this conducting sphere, and we've already seen what the electric charge, what the electric field looks like around this thing. And I'm going to go directly to the diagram here. There really isn't much calculating to do here, but basically we're going to end up with something like this. So I've kind of left myself some space to write here, but I didn't really organize it that well. But this will probably do, basically. Okay, so we know what's going to happen outside of the sphere, right? We know outside of the sphere, it's very easy for us to calculate what the electric field looks like out there. We just use Gauss's law, and when we wrap this thing in a Gaussian surface, we know that the charge enclosed is going to look like a point charge to us, and we're going to end up with the electric field of a point charge, right? And if we look back at our notes, and I don't have the notes up right now, but I will pull them up so that we can refer back to them. 1 second. Right, here we go. Okay, so for, where are the notes that I need? Right, here we go. Okay, so when we look at the notes from last class or from last video, which would have been our second video on electric potential, we wrote down what the potential of a point charge would look like, right? We know that the potential of a point charge is going to look like this. Okay, and that was equation 3 from our last set of notes. And so we know that that's what we're expecting to see here, because we know that the electric field looks like the electric field of a point charge when we're outside of the sphere, right? So we know that our electric field looks like this outside of the sphere, and because we know that our potential, our electric potential, is going to look like this outside. Oops, that's inside. Outside of the sphere, and I circled the wrong one here too. This expression here is outside of the sphere. Okay, but what's going to happen inside of the sphere? So when we think back, we know that we're going to have no electric field inside of our conducting sphere, right? We know that there can be no electric field inside of the conducting sphere, and we can see that by using Gauss's law. If we just draw a Gaussian surface inside of the sphere, it's enclosing no charge, because we know that all the charge has to reside at the surface, right? And so, rightly so, they draw the electric field here equal to 0 inside the conducting sphere. But what's going to happen to our potential, right? What we need is for let's say that there was a charge inside. Let's say we had a test charge inside this conducting sphere, which we can't have in a sort of electrostatic situation. But let's pretend that we did have one. Would it feel any force? Well, there's no electric field, right? So it feels no force. So there's nowhere for it to travel. It's not going to try to travel to lower potential, right? And so it must be true that our potential inside the conducting sphere is everywhere the same as it was at the surface, right? We have no more change in the potential inside the conducting sphere. And that's sort of the most straightforward way kind of seeing how this is going to turn out, right? So inside the conducting sphere we have no electric field, and because we have no electric field, we have no change in our potential, and our potential just remains what it was at the surface, which is basically just this expression. Instead of we swap for small r, we swap in our large R, right? We swap in the radius of the full sphere. So that's basically the solution to what the, well, I mean, this plot here is really the solution to what our potential looks like everywhere around a conducting sphere with some charge Q on it. Okay, so no real calculation there. We're going to see some more calculation as we go on, but this one you can kind of just reason through it by knowing something about the electric field. So maybe I'll point out at this point that it's going to kind of matter. Like if we have knowledge of the electric field beforehand, we can use certain sets of tools, right? We wrote down in our previous lecture, we wrote down an expression. Let me pull it up here so I can refer to it. In our previous lecture, we wrote down an expression, expression 7, where we're talking about the potential difference between A and B, right? We're talking about writing that down in terms of the electric field. We're writing it down in terms of an integral of the electric field dotted into dl, our small length elements, right? So if we know the electric field, we have one way of finding our potential. But if we don't, we also have equation 3 that we can use, or I guess equation 5 eventually that turns into an integral, right? So we develop this integral in equation 5, and we can use this if we don't know about the electric field, but we do know about the charge. So we can integrate over dq we're integrating over dq over r, and once we do this integral, if we know about the charge, we can find out about the potential. So there's a sort of interplay between charge, electric field, and potential that we can use these different variables in different ways to find things that we need, right? So let's keep going with the examples, and maybe some of that will become more clear here. This is example 23.9 from the textbook, and we've looked at the electric field between two parallel charge plates before, but now we're going to look at the potential between these plates. Okay. And so we're starting off. We have two oppositely charged parallel plates, and we want to find the electric potential between these plates. So we want to find the potential at any height y between the oppositely charged parallel plates. So we have a nice diagram here. We have our test charge Q naught. We have some point A at the top positively charged plate up here, which is located at D, a distance D from our bottom plate, where we have a point B and our negatively charged plate there, right? So how can we kind of get to this solution? Well, we're going to start off by recalling from our first set of lectures in this chapter. I believe it was, section 23.1. We wrote down that our electric potential energy, our U, can be written like this. Okay. And so what is this? This is the magnitude of our test charge. This is the magnitude of our electric field, and this is just this distance y. Okay, and this is going back to our first lecture, like I said, on this topic. So we're now going to set a zero potential. We're going to call this bottom plate here at y equals 0. We're going to call this our u equals 0. Okay, so there's no potential at that point, and as we go up away from that point, we're picking up some potential. Okay. Then we also have the definition for our potential in terms of our potential energy that we wrote last class or last video as this here. So we have our potential is equal to our potential energy over the magnitude of our test charge. Okay, that's our definition. So let's just sub in, and this should look more like a V. Let's just sub in our U into this expression here and see what we find. We're going to end up finding that V as a function of y is going to be equal to our test charge times the magnitude of our electric field times our distance y over our Q naught here, the magnitude of our test charge again. Obviously we can cancel these out, and this is going to give us EY. Okay? So the potential decreases in the direction of the electric field here, right? So let's think about that for a moment. So as the charge comes down, it has less and less potential energy until it's sitting at the bottom, and then it has no potential energy, right? And this is again very much in analogy to gravity, because we're dealing with this uniform electric field. It lends itself nicely to our understanding of gravity, because we always think of gravity as a uniform sort of gravitational field that we're sitting in. Not really, but at the surface of the Earth, it's a very good approximation for it, right? And so we kind of see that we're getting no potential as we get close to the bottom, and we have a much higher potential as we get further toward the top. Okay, so let's now set a point A. Well, where we have it on the diagram, we'll set our point A where it's at the very top. So we're going to set y equals d at the very top, and then we're going to have our v at y, which is now going to be a v at d. That's going to be equal to our potential at the top. Okay, and so we can write down the potential difference between the top and bottom. So this is going to be VAB, which is just VA minus VB, and this is just going to be equal to E, and this would normally be a Y, but we know that our VA is all the way at the top, so now it's going to be D, right? Because the distance from the bottom plate to the top plate is this value D here, right? And so we've set our equation up in this way. We can now just rearrange it so that we're going to end up having E is equal to VA, well, VAB, I should say, over D. And let's kind of see what we've written down here. There's no sort of fancy math here, but the result is interesting. What do we have here? What we have here is we have our potential difference between the plates. So the potential difference between our top plate and bottom plate is when divided by this distance between the plates, D, gives us our electric field. So what is this kind of telling us? This is telling us that as we bring the plates closer together, let's say we brought the bottom plate down the bottom plate up or the top plate down, we would reduce D, and if we reduce D in this equation, our electric field gets larger. So this is telling us that if we bring the plates closer together, we have a larger value for the magnitude of our electric field, which is an interesting result, right? So D decreases in value, E increases in value, and vice versa. If we bring the plates farther apart, if D increases in value, then E will decrease in value, right? And so again, I think really the key takeaway from this is that yeah, I mean these results are interesting, but remember that we can do this. We're able to set our zero potential wherever we want to, wherever is convenient for the problem, wherever it allows us to solve things that we're trying to solve for the problem. Okay? Let's take a look at the third example that they look at in the chapter, and they have a little more detail, or a little more calculation, I should say, in this one. But let me first pause and save. Maybe I'll do that after every problem from now on. Hold on one sec. Okay, let's keep going here. Okay, so in this example 23.10, we have an infinite line charge again, and so we've kind of looked at this problem before. We did a finite thin wire, and then we took the limit and we looked at the electric field outside of an infinite wire and stuff like that. So now what we're going to do is we're going to look at this infinite wire sort of from the beginning here, and what we're going to be doing is we're going to be taking our result. So again, we're kind of assuming that we already know the electric field, and we want to find the potential outside of this wire. Okay, so let's do that here. Scroll down a little bit. So that this is our picture here, right? So we're thinking of basically case A mostly, right? So we want to find the potential at a distance r from a very long line charge with linear charge density lambda, right? Okay, so let's start off. We're supposed to know what the electric field is. So our electric field at some distance r outside of this infinite line charge is going to look like this. And this is a result we would have seen before, right? And so now what we want to do is we want to take the expression that we saw, and maybe I should refer to it by its number. We saw expression 7 in our previous previous work, and we want to use it to integrate this electric field to get a result for our potential. So that expression 7 tells us that VAB is equal to the integral from A to B of E dot dl. And so we need to think a little bit about what E and dl are, or at least the directions of E and dl. Well, we know that E is going to be pointing radially away from our infinite line charge here, right? And what is our dl going to be doing? So our dl is basically we're going to be some distance away from this thing, right? Let's say I'll draw a different one. Let's say we're here. We're going to be some distance r away, but everywhere that we're away, we know that our E is pointing in this direction, but we're also our dl is also pointing in this direction, because we're going to be integrating over these small chunks of length here. So in both cases, we have an r hat pointing in our direction here. So basically, what we have is this is going to turn into A to B of ER pointing in the r hat direction, dotted into dr, these small infinitesimal chunks of length in the r direction, in the radial direction outward, also pointing in the r hat direction. Okay, so this dot product basically just goes away. This dotted into this just ends up giving us a 1, and we end up with an expression that looks like this. We have the integral from A to B of ER dr. Okay, and so we can just copy in our ER into this expression, and let's do that. So we're going to end up with a VAB equal to, and now I'm just copying from above, lambda 2 pi epsilon naught. The r is going to have to stay inside the integral, and so we're going to be integrating from, so when we say point A to point B, what we really mean is some r a, right? Some point. Let's say we're integrating from, let's say we're interested in this point here. Let's say we call this A, and our point B is going to be some point far out here that we're going to call B. So we're integrating from what we would call RA to RB. We're going to call this vector pointing from the rod to the point A, RA, and the one pointing to the point B, RB. Okay, so we're going to integrate from RA to RB dr over r, and this r is just coming from the r that we had before, and the dr is just our integration, our dl that's turned into a dr, right? So we need to do this integral. This integral is not too complicated. If you've done this in your calculus class in your 112, you'll probably already know the answer, or you can just look it up. But basically, what you're going to find is that this integral reduces to this, what we have here. So I'm going to write it out here, and we're going to end up with a ln r. This ln r is the indefinite integral of dr over r, okay? And we have our limits of integration here, ra and rb, okay? So what do we end up with? Maybe I shouldn't skip steps here. We're going to end up with, so when we evaluate this, we're going to end up with a ln rb minus ln ra. And we know we can use the laws of these logs to be able to write this as well, I'll rewrite it here as this expression here. Right? So we can rewrite it like this, and this is our VAB. This is our potential difference between the point defined by RA and the point defined by RB. Okay? So let's now take a closer look at this. So what do we really mean by this VAB? Let's remember that VAB really means VA minus VB is equal to the expression that I just wrote down. I'll write it again. Like that. Okay? So usually we're free, and I mean we are free in this case too, to choose where we want our zero potential to be, right? So we might be tempted to say, well, we're just going to set our zero potential out at infinity. So we can say we can let this RB just run out to infinity. We're going to say at infinity this thing is going to be 0. We're going to have no potential at infinity. But we run into a bit of a problem here, right? If we do that, then we're kind of forced to set RB to infinity, okay? And if we do that, this thing is no longer useful to us. This thing just blows up, right? We just end up taking the ln of infinity, which is just going to give us infinity, and the whole thing doesn't work. We have an infinite potential at VA at, well, we have an infinite VA potential at RA. So our potential here would be infinity. That's no good. So we're going to have to choose a different point at which to set our 0 potential. So we can set our 0 potential for any point. Let's say we just choose some point. We're going to set RB to R naught. This is some point where R naught is greater than RA. So basically some point, some finite point out here that is greater than RA, but it's not out, not out way far at infinity, but somewhere closer by, some finite distance away. If we do that, then we're going to find that we set, basically I'm going to rewrite this equation here. We're going to find that we have this equation here again. Except now we're still setting our 0 potential, so we're setting our 0 potential, but we're setting it at R naught. Okay, so that's not an RB anymore, now that's an R naught. And so what this ends up giving us is this gives us an expression for our potential with a 0 that we've selected, some finite point at which we're calling that 0 potential, and it gives us an expression that we can talk about what our potential is everywhere else in relation to that point. So we end up with an expression that looks like this. And that will be our final answer. Okay, so we have our potential at a point R, at some distance R from our infinite wire, and we're setting our 0 potential at R naught. Okay, and so why do we run into this problem? This is a problem we want to keep in mind because we're gonna come back to this problem a couple of times here. So we ran into this problem because we're trying to set infinity, well, we're trying to set our 0 potential at infinity, but we're dealing with an infinite wire. So these two infinities kind of clash. We end up in a situation where we can't really write a solution that makes sense here. So we have to pick a different point, and in this case we can easily pick this R naught, and everything works out fine. But what if we wanted to do this differently? What if we were dealing with a different situation? What if we wanted to deal with a non-infinite wire? The textbook does look at a finite wire when you're close up to the wire in the last example that they do in this chapter. I'm not going to do that example in this video. I'm going to do it at our next meeting, or whenever the meeting is scheduled to be done for a discussion on this section. And in that one, we're going to take a look at the integral kind of more closely. In the book, they kind of take the easy way out and they just look up the integral. We'll actually go through. We'll do the integral. It's certainly within our reach. It's a little bit long, but it's definitely sort of handleable for us. So I think it's definitely worth looking at, and we'll do that. I'm going to move on to the next example here. Before I do, let me just pause one more time. Okay, and we can get back to our example. So let's take a look at example 23.11 here. Okay, so in this example, what do we have? We have an electric charge Q. It's distributed uniformly over a thin ring of radius A. We want to find the potential V at a point P on the ring's axis, a distance x from the center of the ring. So basically the setup that we have here, we know what the charge is over the ring. We know what A is. We're looking for the potential at some point P at a distance x, which sits on the axis, right? So that's all great. In this case, though, however, we're going to assume that we don't know, although we do know what the electric field is, but we'll assume that we don't know what the electric field is, and we're going to start from scratch, and we're going to calculate what our potential should be. Okay, so we're going to use, and I've forgotten again, I think it's equation 5 from the notes. So we're going to use equation 5 from last video's notes, which basically tells us V is 4 pi epsilon naught times the integral over dq r, right, like that. And so this allows us to calculate our potential without any prior knowledge of the electric field. Okay, so we can pretend like we don't know what the electric field is outside of this ring on this axis, and let's do the calculation, right? So let's take a look at this. And I should probably mention before I start writing this out that we could have done exactly what we're doing here in the case of our infinite rod here. We could have again assumed we didn't know ER, and in a sense we're going to do that for the finite rod when we take a look at that when I do that in a couple of days here. So let's start off with this though. Okay, so we have this expression. What is R here though? Okay, so we know how to calculate V, but we need to know what R is. R is just this expression that we have up here, right? So R is just going to be our distance from the chunk of charge that we're calculating from out to the point where we want to find our potential, right? We're given R here. We could have easily calculated it, but since it's given to us, let's write it down. We've got 1 over 4 pi epsilon naught, and again we're doing the integral from over dq. And our R is now going to be the square root x squared plus a squared. Okay. So this could have ended up being tricky, but it's not going to be in this case, because if we think about it, let's think carefully about what dq is here. Can these tiny little chunks of dq have any x or a dependence, right? Well, not really, right? Because no matter where we go on this ring, a is fixed. A is always just going to be a. It doesn't change as we integrate around dq, right? It's always a because of the shape of this ring, right? And x is always x, right? We're not changing the distance x at all here. X is always going to be this constant distance x. So because of that, we can factor out our denominator here, and this is going to make the problem extremely easy. Because once we do that, so we're basically going to end up with this. And then we just have the integral of dq. Well, but what does the integral of dq really mean? We're just integrating over all the little chunks of charge. We haven't translated dq into anything. We would often have to go through and translate dq into stuff, but that's only if we have other stuff in there. If it's only dq on its own and we're integrating over the whole ring, we're going to pick up all the contributions of dq's that there are, and if we add up all the dq's, what does that end up giving us? Well, that just ends up giving us q back, right? We just add up all the little chunks of charge and it just gives us back our total charge. And that's basically it. We've basically solved the problem already. So we end up with a situation where we can just write out the solution. It looks like this. Right, and that's our solution for our potential at a point P somewhere along the axis of our ring. Okay, so that's the kind of easy way to do this. Now the textbook doesn't go into this, but I am going to go into this here. What if, and my notes are a big mess here, so bear with me if I have to sort of dig through them a little bit. But basically, what if we did know the electric field outside of the ring, as we do, we've calculated this before, and we wanted to go from our knowledge of the electric field to a value for our potential, right? We would expect these values to match, and if I do this right, they will. So let's take a look at what we have. Okay, so we know from equation 7 from our previous notes that again VAB is equal to the integral, and I'm going to say from point A to point B like this. I'm using a capital A and a capital B because we already have a lowercase a in here, and I didn't want to confuse the two. So let's say we go from A to B of E dot dl, right? And let's think about the ring here, and let's think about what we're kind of being asked to do. We know what the electric field is at this point. Well, at any point along this axis, right? This time we're looking at some point a distance x out from the center of our ring, right? The electric field there is only going to point in this direction, right? Only in the direction of our axis, right? In this direction, or conversely, if we were going out this side, it could point in the opposite direction, right? But we know it's going to be pointing in that direction. Also, we're integrating And now we have to be careful. This dl, we're integrating from whatever point we choose. So let's say we chose a point P here, like this one, but now this point P will become named A, right? Because we're integrating from A out to some point B, which would be out here, which we're going to choose as our zero potential, right? So as we're integrating over all these little chunks of line, what direction are those pointing in? Well, they're again only going to be pointing in the direction of this axis, right? And because of that, we're going to end up having a situation where E is always parallel to DL, and so this simplifies our integral a bunch, right? We could get rid of that dot product. We're going from A to B, E dl, right? And we can at this point write down what E is. We know we've calculated this before. We can look it up in our notes. Our E is a function of R, and I'm not going to write it as a function of R. I'm going to write it as a function of X. So our E as a function of X is going to be 1 over 4 pi epsilon naught. And we've seen that we have a Qx over, what was it, x squared plus a squared to the 3 over 2, right? So this is a result from our first module, right, when we did the integral around the ring. Okay, so that's our old result. And what is our dl? Well, our dl is just going to be dx now, right? We're just integrating along this, right? So every little chunk of line segment is just giving us a little step in the x direction. A little dl is a little dx, right? So if we substitute both of these values into the integral, what do we end up with? We end up with basically this. We have VAB, which we know is equal to VA minus VB, right? And I'm not going to put the limits of integration on right this second. Well, okay, I'll write them like this, but I'm going to change them in a second. And this is equal to 1 over 4 pi epsilon naught. We'll be able to factor that out in a second. We have a Qx over x squared plus a squared. This is all to the 3 over 2. And then we have a dx here, right? So we can clean this up, but first let's talk about the limits of integration. We want to pick a zero potential because we want to be able to get rid of this VB so we can talk about the potential at only that one point, right? So let's say we set our zero potential, and because we're dealing with a finite ring here, right? So we have a ring that's not infinite in size. We're going to be safe if we set our zero potential out at infinity. So let's do that. Let's set our B an infinite distance in x away from our ring. So let's set B at infinity, and let's set A at some value, whatever value we want, x. Okay, and again, we're going to get into the situation where we're integrating in x, and one of our limits is x, but that's fine. It's going to work out fine in the end. Okay, so this is basically the integral that we want to do. Let's clean this up and take a look at this. Now because we've eliminated VB, I'm just going to call our VA our potential, our V. And so we're going to end up having to do this integral here. We're going to have Q, which is going to factor out 4 pi epsilon naught. And then we want to do the integral from x to infinity of x dx over a squared. Oops. Yeah, it's fine. Or maybe I should keep it the same. X squared plus a squared 3 over 2, right? So this is the integral that we want to do, and we have seen this integral before. We know that we can do this this integration by a simple substitution here, and so the substitution that we're going to make is we're going to let u equal x squared plus a squared, which is going to mean that our du is going to be 2x dx, and we want x dx, and that's just going to be du over 2. Right? So let's substitute all this stuff in there. We're going to end up with an integral that looks like this. Q over 4 pi epsilon naught. We're going to have, oh, 1 sec, got a little noise here. Perfect. Okay, so we're going to end up with this stuff factored out. We're going to be able to factor out this factor of a half that's going to come from our substitution of du into this, right? And so we're going to have a factor of a half out front. We're going from x to infinity, but this is kind of weird, but it's like x equals x, right? And we're doing the integral of u to the minus 3 over 2 du, right? Well, this is just going to end up giving us a value of minus 2u to the minus, and I can kind of rewrite this again. I guess I can add more pages if I need. So let me rewrite it fully here. So what we're going to end up with is q 4 pi epsilon naught. We're going to have this factor of minus 2 that's going to come out front, so we're going to have minus 2 over 2, right? And then we did the integral. I'm just going to move our u back into the basement here, and let's remember, u is just x squared plus a squared. So what we're going to end up with is 1 over square root, because it's to the power of minus a half, right? X squared plus a squared, right? And this is all going to be evaluated at x and infinity, okay? And so we're basically there. We just need to evaluate at our limits here. We might be a little bit worried that this infinity is going to give us some problems, but it's not going to. We're going to see why not here in a second. So we end up with, and let's remember what we're calculating, this is v. So we end up with a q over 4 pi epsilon naught. We're going to have a minus 1 here. And our two, so let's start off by looking at our upper limit here. So we're going to end up substituting infinity into here. Our x squared is going to basically go to an infinity squared. This whole thing is going to end up killing off this term, and so this thing ends up being a 0, right? Because our denominator is going to infinity. And when we do our x substitution, so we need to subtract our evaluated lower limit here, we're simply going to end up with this expression here, right? These two minus signs are going to cancel. Obviously, we get nothing from the 0, and we end up finding this result here. Okay, and if we've done everything correctly, that result should be the same as this result. It is, that's great. And so we can see that we can either start from scratch and integrate over the charge to find our potential, or if we know the electric field, we can integrate the electric field to find our potential also. Okay, so there's two different ways to find our potential at a point. And sometimes this will work easily. Sometimes one way will work better than the other, and it really depends on the problem that we're looking at. And as I said, I'm going to look at the final example. We're going to go into a little more in-depth analysis of that final example from this section when we meet. But I'll leave that for when we meet, and I'll see you guys in the next one.